Hey everyone, how are we doing? Yes, perhaps. Why is he moving there? Anyway, football is important. Football doesn't exist for us at the moment. It's just chemistry, maths, and biology. I'm okay, I'm in the office. Hopefully the color looks better than normal when I'm in here. Normally it's flickering of some sort, but it looks stable today. First things first, how are we doing? Are we well? Are we anxious? Are we nervous? I shouldn't have asked that. Hello, hello, hello. Not the shimmering hair today. I'm not that grey. Not that grey. Hello, hello, hello. Chiwendu, greetings. Edix, Nessa, hello. Right. Remember, a little bit of pressure and anxiety is good. Means that we care. Hey, QP, how are you? Hey, Manpreet, how's it going? Let's just start, shall we? Let's get cracking. Okay. Oh, well. Right. Chiwendu, what do you mean finally? Of course you can. You're free to join whenever if you got the link. Hello. Maths and biology scary. Pressure makes diamond. Absolutely. Hey, Chloe, how are you? Right, so I thought we'd just do a lot of the stuff that you wanted yesterday, and let's just get cracking. Make sure you got a calculator ready. So let's go. You don't have the workbooks, but that's okay. Let's see how it goes. So steel is a mixture primarily composed of iron and carbon. Correct, Amundo. So a group of students carried out a titration to determine the percentage of iron present in a steel wire sample. Okay. To begin, a known mass of steel wire was reacted with dilute sulfuric acid. Okay, so what I might do, let's do a little storyboard while we're here. Okay, so I've got some steel. I know it's a wire, but I'm just saying that's steel. Hey Zuriel, how's it going? And I'm adding it to sulfuric acid. And then I'm topping it up in a volumetric flask to 250 centimeters cubed. Okay, cool. Amuri, not gonna have time. We'll just do it like this if that's okay. So you can read the question, have a go on some paper, or if you've got an iPad or whatever. I won't have time. I won't have time. Oh, we don't need to know the volume of H2SO4. It's not important, but we're just acidifying it because it's a redox reaction, I'm guessing. So that's why we're adding sulfuric acid, because it's the source of H plus ions, and to make the Fe2 plus. So we top it up to 250 mark. Okay, cool. So the reaction that takes place is given to me in the question. So then what we do is we take 1/10 of this out. So we have a 25 centimeter cube portion. And then we're doing a titration with what? What's in the burette? It's a beautiful purple color. KMNO4, absolutely good. Okay, so we've got to describe the color change that's observed at the end point of the titration. So I guess the question I'm asking is, what is the color in the conical flask to begin with? Yes, absolutely. So it's starting off colorless, right? But at the end point, we can't say clear. We have to say colorless, okay? If you say clear, you won't get the mark. That's not a color. Because you can have a colored thing and it can also be clear, which is referring to transparency. So when you have one excess drop of, no worries, all good. So when you have one excess drop of the KMNO4, well, then it's going to be pale pink at the end. So it goes from colorless to pale pink. Okay, light pink, you'll definitely get the marks for light pink. Okay, what do we think? By drawing this out, which took best part of what, 30 seconds, that allowed me to answer this question and get that mark. Hey, Drita, how's it going? Drita, man, greetings. We got a nice little crew. We've got a nice little crew who's turning up. I like it. So that was only one measly mark. Yep, always do the storyboard if you can, okay? So let's have a look at the next bit. So this looks like a 5 mark question. Do you see it was on Teach Floor? It was. I did put it on Teach Floor last night, but don't worry too much. So a student measured out 1.53 grams of the steel wire using a balance and carried out the titration, and they got an average titer, so a mean titer of 27.35. Yes, Drew, you had to just copy and paste it in. And then it had a concentration of the manganate solution of whatever's in the question. Okay, where do we start the calculation? What's step number 1? Yep, moles of what? Moles of MnO4? Yeah, QP, it's very similar. So we work out the moles of MnO4 minus. So to work out the number of moles of MnO4 minus, what do? We take the concentration, which is 0.0195. We multiply it by the average, which is 27.35. Over 1,000, done. No, we're not just doing titrations today. We're going to do a mixture of things. We'll just see how much we can get through. Right, what do you guys say? I get 5.33325 times 10 to the minus 4 mole of the manganate. Okay, cool. So where do we go next? So if we go back, that's the number of moles here. And I've got some Fe2 plus in there. So where do we go next? And you have to use equations 3 and 5 to help you here. So you don't have to write them out. They've given them to you, but they haven't done one thing. Check to see if it's a 1-to-1 ratio. Absolutely. But is it a 1-to-1 ratio? Oh, Nessa, because that's how much KMNO4 we added. So we added whatever it was, 27.35 from the burette. Does that make sense? Okay, yeah, exactly. So just don't assume it's 1-to-1. So we have to scale this up by a factor of 5, right? Because this has to be a 5 electron oxidation, because this is a 5 electron reduction. So they've combined it with electrochemistry here, which they could do. So therefore, the ratio of MnO4 to Fe2 plus is 1-to-5. So the next step is, let's work out the number of moles of Fe2 plus in the conical flask. And that's in a 25 centimeter cubed sample. Nope. Well, they've kind of helped you, but you had to do some work for it. They didn't give it to you for free, okay? So it is 5 marks. So then all we do is 5.335 times 10 to the minus 4 times 5. So where does that take us? Yeah, 2.67 mole. Okay, so we've got the number of moles. So we've got the number of moles of iron 2 plus in the conical flask. So where do I go next? So drawing the storyboard helps. So I've got the number of moles in the 25 centimeters cubed, but I want to work out what's in 250. Absolutely nice, guys. So you multiply it by 10. So then the number of moles of Fe2 plus in 250 is going to be 2.67 times 10 to the minus 3 multiplied by this scale factor of 250 over 25. So we're just timesing by 10, which is 2.67 times 10 to the minus 2 mole. Okay, then where do we go next? So I'm after the mass of iron. Okay, so if I'm after the mass of iron in the steel sample, I've got the moles. How do I go from moles to mass? I times it by the Absolutely. The AR of iron, which is what? It's going to be 2.67 times 10 to the minus 2 multiplied by 55.8. So what do we get? Quite a big number. Do we get 1.49? What? Okay, cool. So that's the fourth mark. So what is the final step? So now I can work out the percentage. So the percentage is going to be 1.49 over the total mass of the steel wire, which is 1.53, times it by 100, and what do we get? Do we get 97.3 or 97.4? Yeah, 97.3 and 97.4, whatever. Depends on your rounding. Does that get me the mark? Is that to 3 significant figures? Yep, it is to 3 significant figures, and we move on. Let's go. Thoughts on the question? Are we happy? Like, if we see a question like this, are we going to be thinking, oh dear God, or are we going to be thinking, yes, I am going to dispatch this question? Yeah, easy 5 marks. All right. It was, exactly. All right, let's go. 97.3 and 97.4, both are allowed depending on whether you rounded early or not. Yeah, I rounded early. Doesn't matter. You still get it for 97.4. Okay. So a chromium-based ionic compound label X appears orange. Okay. Straight away, when I'm thinking of oxidation states, do I know any chromium species which appear orange, and what is the oxidation state of those species? Yeah, Cr2O7 minus, and in Cr2O7 which is orange, chromium is in the +6 oxidation state. So chromium +6 is orange. Okay, just as a bit of revision, when it's reduced to chromium 3+, what is the color of chromium 3+ then? Green. Yep, absolutely good. Okay, so and I'm thinking about organic as well when I'm reading this. So got the following percentage by mass calculation. That is not -11. That is 11. Okay, so these are my percentages. So I got to determine the empirical formula. Okay, cool, let's go. So nitrogen is 11.11. Have a go yourselves as well. 3.17. Chromium, which is 41.27. And oxygen, which is 44.45. Okay, cool. So then what are my ARs? Well, I'm going to divide these by the AR to get the number of moles of that element in the compound. And chromium is what, 52? Yeah, and oxygen is 16. Okay. So that's going to be 3.17 moles. So what? Do we get 0.79357? Let me know if I'm making any mistakes. That's also 0.79365, so it's probably 1-to-1 with chromium and nitrogen. So 2.778 for the oxygen. Okay, cool. So now what I'm going to do is divide by the smallest, and do we agree that the smallest is this one? So let's just divide everything by that. Bit boring, but show the examiner you know what you're doing. So that's going to be 1 and that's going to be 1. Okay, what's my hydrogen ratio then? Is that 4? I've got no idea. Yeah, close enough to 4. Okay, and then what's my oxygen? Does my oxygen work out as 3? 2.778 divided by 0.79357. Okay, looks like 3.5 to me. So then what do we do here? Yep, absolutely. Then we times by 2 for all of them. So this is going to be 2 to 8 to 2 to 7. Done. So if I'm writing the empirical formula of X is going to be N2 H8. This was I think this was 8 marks. I can't remember. But it's old spec. Absolutely, Nafisa. So H8Cr2O7. That's the empirical formula. Okay, cool. So compound X is an anhydrous salt with no water crystallization. Okay. Cool. When compound X is gently heated, it breaks down to produce 3 substances, Y, Z, and water. Okay. Substance Y is a green chromium oxide with a relative molecular mass of 152. What could that be? Increase from what, 90 to what, 95? Okay, let's continue reading because it's a bit of a tricky question. So substance Z is a gaseous product. At room temperature and pressure, 1 decimeter cubed of Z has a mass of 1.17 grams. Okay, what are we going to do to calculate this? So I'm thinking that the volume is equal to the molar volume times the number of moles. Agreed? So what could I do here? Okay, but let's go through it. Let's go through it. So what do we think? Any suggestions? What could we do? Okay, well, do I know the volume? Maybe, Chimendu. But let's just do this bit. I'm looking at the gaseous product first. Just want to get that calculation out of the way. So I've got 1 decimeter cubed of it, so I know the volume, and I know what the molar gas volume is as well. So what's that going to be? Yeah, let's have a look. So 1 over what, 24? So 24th. So that should give me the number of moles, and then... Okay. Yeah, so that's what I'm thinking. So to get the number of moles, I'm going to do V over Vm. V is given to me, which is 1, and the molar gas volume, which is a constant, is 24. So the number of moles is 1 over 24. We're going to leave it as a fraction. In fact, no, I'm not, because it annoys me. So it's 0.04167 mole. Okay, but I also know the mass of Z. So if I know the mass of Z and I know the number of moles, what quantity can I determine? Well, I can determine the MR, right? So the MR is equal to the mass over the moles. So it's going to be 1.17 over 0.04167. So what does that give us? Yep, 28.1. So it's a gaseous product which has an MR of 28. So what are we thinking straight away? What gas do you know which has an MR? Yeah, absolutely, Kirsty. It's N2. Good. So therefore, N2. Done. What I'm going to do is just rub out that first bit for the empirical formula. Don't need that anymore. So I figured out what Z is. Tick. I know what the empirical formula of X is. So now let's have a look at Y. So Y is a green chromium oxide with a relative molar mass of 152. Okay, so what do we think this oxide could be? I think, was it Chinwendu who said it could be Cr2O3? What do we think? Let's guess and say Cr2O3. Because I know that chromium in the +3 oxidation state is green, so it was worth doing that bit at the beginning, okay? So if that is +3, I need 2 lots of the chromium, and I need 3 oxide ions, so it could well be Cr2O3. So what is the molar mass of Cr2O3? Does it add up to 152? So 52 times 2 plus 16 times 3, does that give me 152? Well, if it gives me 152, hurrah, I'll take that. Whoa. Hang on. Bear with me, I have no idea what's happening. There we go. Cool. Well, I didn't just know. I actually had an idea though, didn't I? Why did I have an idea? Because I know that Cr3 plus is green, and it tells me it's a green chromium oxide. So it's a little bit of organic knowledge and transition metal knowledge as well, right? It's not just blind. So I know that chromium 3 plus is green. That's how I knew. So I'm saying that Cr3 plus is one of the ions. So if Cr3 plus is one of the ions and I'm combining it with an oxide, well, I know that the oxide is 2 minus. Agreed? So therefore, what's the lowest common multiple? Lowest common multiple of 2 and 3 is 6, so I need to make this +6 overall, and that -6, so I need 2 of these chromiums and 3 of these oxide ions, and bosh, done. That's how I know it's chromium oxide and chromium in the 3 plus oxidation state. So I'm not just going off nothing, okay? It's based on some knowledge. Does that make sense how I've done that? Arvind, no worries, you were forgiven even though you were doing biology. Cool. So that's sorted. So we know what Y is. Okay. Done that, and we've done that. Okay, where do we go next? Okay, tell me what to do next. Yeah, let's write the formula. Right, I have no idea what's going on with my pen. It's acting up a little bit, so bear with me. The nib is being funky. So we've got to determine the empirical formula of X. We've done that. Identify the ions present in compound X. Okay, and state its ionic formula. Okay, so what's the ionic formula going to be? So what do we think? It's a really good question. One of the answers is staring us in the face. We don't actually need to do two half equations. In fact, if you look on the screen, it's got no water crystallization in there. Yeah, oh, and it's close. Well, look at this. Do I have 2 chromiums and 7 oxygens that I had in my empirical formula? Look. Yeah, so that's going to be existing as... Apologies, let's try and fix this. Well, not ammonia, but close. This is going to be existing as... Cr2O7, 2 minus. That's going to be one of the ions there. So the other one that's going to be there to balance this out, so I need nitrogen and hydrogen. What about if I have NH4 plus? Yeah, exactly. It's the ammonium ion. But how many of these ammoniums do I need? I need 2 of these. Exactly. So it's a really good question. So the formula is going to be what? So the ionic formula is... Well, the ions in there are NH4 plus and Cr2O7, 2 minus. So those are my ions present. Does that make sense? So then I've got to write an equation for the decomposition. And the equation for the decomposition is going to be NH4 twice Cr2O7. So when I decompose that, what is the green oxide that I get? What's the formula of the green oxide? That is Y, absolutely. So it's Cr2O3. Correct. Okay, where do we go next? So that is definitely oxide. It tells me I get some water as well, right? I think. Yeah, so I make some water. So I'm just going to put H2O down. And then I also know that I generate some N2. That's good. So I can put N2 down. So let's put N2 there as well. There it is. Okay, so how do I balance this up? I clearly need 4 of those. And I believe that balances everything. There we go. So cracking question. So you're getting 1 mark for here. You are getting another mark for that. 2 marks for that bit. 2 marks for the ions. 1 mark here. So where does that take us to? 5. I think another mark here. And I think there was a few more somewhere else. But there's a lot of going on. This question was low-key fun to do. Absolutely. What do we think? Good question or horrible question? Because it tells me... Well, look, if it does come up on paper 1, if it does come up on paper 1 and we've done it, you should be thinking, yay. You shouldn't be thinking horrible. If a question like this comes on paper 1, amazing. Manpreet, ever the optimist. So, how did I know it was Cr2O3? Because it tells me, it gives me a little clue. It tells me that the oxide that we form is green, and I know that chromium is green when it's in the +3 oxidation state. It's from old spec. Old spec, variation of an old spec question. So not new spec. Cool. Let's go. Well, what did we say? THFE yesterday. Train hard, fight easy, right? So let's go. Cool. We've got to write the simplest possible half equation for the oxidation of hydrogen peroxide in these acidic conditions. Okay, so nice little question because they flipped what's going on, okay? They normally say from 2 half equations. So just answering Edix's question. So chromium 3 plus and chromium with any oxygen would both give green. No, so normally CR... Whoa. So normally CR3 plus is green. Chromium is going to be metallic looking. Chromium is going to be metallic looking. Chromium 3 plus, whether it's bonded to oxygen or other things, is most likely going to be green. And CR6 plus is going to be orange. And one chromium 6 plus species that we know is this one, the dichromate ion. So that's what it was saying. You have to figure out, it's telling you it's an ionic salt, so it's going to be made up of an anion, and that's the anion. So you have nitrogen and hydrogen left over, so that's got to be the cation, but you need two of those to balance it out. Well, yeah, essay subjects are even worse, right? Absolutely, you've got to approach it like we're doing in class. All right, so this is a question where they flipped it. So they've given you the overall equation, and you've got to determine what one of the half equations is. Can I be honest? I don't read all of it. I actually go to the end bit, and then I figure out. I actually go to A, and then I work backwards. So I'm looking for key things if you do enough of it, but you guys need to go slowly and just take your time and read. You've got to read the question. Don't do that unless you're very confident, please. But please read the question. Okay, so what's going on is I'm looking at my peroxide. So what species? I think it's more efficient if you've done enough practice, but I think if we are playing it safe, read from the top. So I'm thinking, well, we're not multiplying the top one by anything because they've given us the overall equation here, right? So what they're saying is, this is the reduction reaction. So what's the oxidation reaction from the overall equation? H2O2 is an oxidizing agent. So it's actually reduced. So I know from the above that the MnO4 minus goes to Mn2. Agreed? And H2O. So the Mn2 plus and H2O are coming from the reduction. So this is coming from the reduction reaction. Whoa. And this is also coming from the reduction reaction. So where is this O2 coming from then? Where is this mystery O2 coming from? Well, the O2 must be coming from where? Not the air, but it's coming from the oxidation reaction, which is all to do with the hydrogen peroxide, okay? From your brain. Maybe, but in this one, it's coming most definitely from the H2O2. So that species is being oxidized, whereas this species, the manganese, is being reduced. When you look at it like that, it makes a little bit more sense, right? So now I've got to make a little equation of what's going on. So my H2O2 is forming what? It's forming O2. Alex, it's very possible to get a question like this because this is inorganic / redox. So if you distill it to this, it's balancing a half equation. So okay, so where do the 2H plus go? Tell me, guys, left or right? If I've got 2H plus on the right, what other species do I need on the right-hand side? Good. And, okay, one electron on the right-hand side, agreed? Two electrons on the right-hand side, absolutely. So if we are thinking like chemists, why did they go back and why do we have a coefficient of 5 next to it? Why do we have a 5 here and a 5 here? Absolutely, it's been scaled up, right? Because we need the right numbers of electrons to balance the electrons. Absolutely. So we've got a 5 there. We've got a 5 there. We will have a 10 there, but I'm sure it cancels out with the manganese ones. And we've got 10 electrons here as well. Sorted. Cool. Right. So we've done that one. Where do we go next? Okay. Everyone's okay, so Edix, the answer to that one is, if we have a look at this, if you look at the equation at the top, circle what's similar, okay? What's an A level? Yep, that's a really good question. Right. So we got the manganese, or the manganate, I should say. That's similar. Beng, if you don't mind, was his name, wasn't it? Right. The H plus is also in the manganese one. The electrons are in the manganese one. And then if we go to the product side, the Mn2 plus is in the manganese one, and the water is also in the manganese one. So do you see what's happening? That one's being scaled by 2. Ignore the H plus. That one's also being scaled by 2, and that one's also being scaled by 2. So that's purely coming from the manganate reaction. Does that make sense? So therefore, what we're left with must be down to the oxidation reaction. So the oxidation reaction is all to do with that. So in this case, what are we actually doing to... So I said hydrogen peroxide is an oxidizing agent, but in this case, what is it doing? It's actually giving out electrons, right? So if we go back to our thing, if it's giving out electrons, it's behaving like a what? A reducing agent because it gets oxidized. So the manganate must be a stronger oxidizing agent because it gets reduced. I don't know what a domain expansion is. Your teacher sounds way smarter than me. Cool, let's go. All right. Let's have a look at B. So this is a similar question to what we did yesterday. Okay, so where are we going to start then? So a student is measuring out some hydrogen peroxide solution. Okay, so when I'm reading this, this is the neat hydrogen peroxide solution, okay? So we've got a bottle and here it is. So this is the unconcentrated H2O2. I'm not going to use C1V1 and all that jazz, okay? So let's draw a little storyboard. We dilute it by adding distilled water. So we dilute it, so we're reducing its concentration, right? So where do we go next? And we make the volume 250 centimeters cubed. Okay, so what do we do once we've made the volume up to 250 centimeters cubed? True. And what portion did they take out? They took out 1/10. And then they titrated it against KMnO4. Okay, so I'm sure we know some information. So what information do we know? So what do I know about the KMnO4? I know the volume and the concentration. So the first thing I'm going to do is work out the number of moles of what? Absolutely. Conc and volume to work out the moles. So the number of moles of MnO4 minus, let's go. Okay, so the number of moles are going to be the volume, which is 23.45 over 1,000 multiplied by 0.02. What do we get, guys? Do we get 4.69? Cool. So what's step number 2? So now what we've done is we've worked out the number of moles coming from the burette. So we worked out the number of moles of manganate there that we transferred into the conical flask. Well, what's in the conical flask? I know that there's H2O2 in there. So how am I going to work out the... Yeah, absolutely. Check to see if it's a 1-to-1, or check the ratio, right? To get the number of moles of H2O2. Absolutely. So what were the number of moles of H2O2? I can't remember. So it's a 2-to-5 ratio. Okay, so it's a 2-to-5 ratio. So what are we going to do? How are we going to work out the number of moles of H2O2? Times it by 5 over 2. Absolutely. So the number of moles are going to be 4.69 times 10 to the minus 4 times 5 over 2. So do we get 1.1725 times 10 to the minus 3 mol? Looks good to me. Okay, so that's the number of moles of H2O2 in here, in the 25 centimeter cubed portion. So I want to know how many moles I've got in this larger 250 centimeters cubed portion. So what's that? So the number of moles of H2O2 in 250 is going to be what? Yeah, absolutely. We times it by 10. There's 1.1725 times 10 to the minus 3 times 10, which is 1.1725 times 10 to the minus 2. So that's the number of moles here. And all of that came from where? All of that came from here, right? All of that was in the undiluted sample. Agreed? So that must be whatever it is, 0.01725 moles in the undiluted sample. So how do I work out the concentration in the original? Ooh, times it by the MR to find the grams. Absolutely. So we've got the number of moles. So we've got the number of moles in question. And I also know the volume, but I want to know the mass of H2O2. So the mass of H2O2 is going to be equal to 1.1725 times 10 to the minus 2 multiplied by the MR. And what is the MR? We could do that, Charlie, but it's asking for grams per decimeter cubed, so I'm going to multiply by the MR here. Absolutely. So times 34. Okay, cool. So what do we get? So do we get this mass, 0.39865 grams? Yay? Okay, but then I need to find the concentration in grams per decimeter cubed. So how am I going to do that? Absolutely divide by the volume. So I've got the mass. And what was my original volume of my undiluted? Was it 25 centimeters cubed? It wasn't 250, Sarah, because we took out 25 centimeters cubed of hydrogen peroxide solution, which was undiluted. It wasn't 250. So if we read it, how does this read? A student measured out 25 centimeters cubed of hydrogen peroxide solution, which was undiluted. Full stop. Don't apologize, that's fine. So they took out 25 centimeters cubed here. Then they diluted it. But the same number of moles that you had here are going to be in here and are going to be in here. But until you get to this point, then you're going to have a tenth of those. Okay? So then let's see what the concentration comes down to. So it's that number of mass divided by, times it by 40 anyway. So do we get 15.946 grams per decimeter cubed? Lovely. Remember to read the question and draw a little storyboard, okay? So if I was annotating this properly, that would have said the volume is 25 centimeters cubed originally. Okay? That is quite concentrated. Do more. Look at all of the past papers and all the past work we've done. You've got help there, okay? You actually have help there. So then, we actually haven't finished. This was a whopping 6 marks. So then I need to work out what? Yeah, moles per decimeter cubed or grams per decimeter cubed can be either. In fact, for what would the moles per decimeter cubed be? So the concentration in moles per decimeter cubed would be the number of moles that we had divided by this volume, which was 25 centimeters cubed. I wonder what that would give us. Still going to be pretty high. So what, 0.469? Not that bad. Does that make sense? So there are two ways of doing the concentration. Okay, so next I need to work out is the volume of oxygen gas released during this redox. Measured at room temperature and pressure. Okay, cool. So how do we work this bit out? You can just divide that by the MR to get the moles per decimeter cubed as well. Absolutely. Where does it say 250, Chloe? In all of the working, I don't think it does. I think it says 25. So we're looking at the undiluted concentration in that step. Okay, no worries. So next I have to determine the volume of oxygen. Okay, so if I got the number of moles of, what do I have the number of moles of? H2O2. Cool. How do I work out the number of moles of O2 then? In fact, this is actually quite straightforward. So the number of moles of O2, it was 5H2O2 to 5O2. Yeah, so we look at the molar ratio. If it's a 5 to 5 for H2O2, what does that mean? It's the same as the H2O2, absolutely. But this is for the this is a good question. Which one am I going to use? Am I going to use that number or am I going to use this number? Because it's asking us about the redox titration that occurs. Am I going to use the number of moles from 2 or the number of moles from 3? Am I looking at it from 25 centimeters cubed or 250? We're not going to use words like limiting here, but where does the reaction occur? Absolutely, it's the 25 because the reaction occurred in the 25, okay? Yeah, absolutely. So we're using this number of moles. Or if you wanted to be safe, you could use the manganate number of moles. So you could have used the manganate number of moles and then worked out the oxygen number of moles, and that would have been a safer way to do it, okay? So if you want to do it that way, you can say that the number of moles of O2, don't know why that keeps happening. So the number of moles of O2 are 4.69 times 10 to the minus 4 times 5 over 2, which is equal to 1.1725 times 10 to the minus 3 mole. Okay, so then how do I work out? Yeah, I know it is being a bit weird. I'm in the office, always is. So then how do I work out the volume of O2? Remember this equation, V equals the molar volume multiplied by the number of moles. So the volume is equal to 24 times that. So what do we get? Hang on. Yeah, is it 0.02? I'm still here. I just thought I'd show you. I think it comes out to 0.0281 decimeters cubed. Absolutely. But what do we think about the question? It's not that bad. For 6 marks, I say it's okay. What are your thoughts? Let me know in the chat. I'm still here. I'm still here. I just went away so you can see what's going on. Wow. TW. Wow. Very good. Okay. Any questions? Is it okay? Wicked. All right, let's go. Nice. Okay, no idea what's going on with this, but who cares? Let's have a look. So now I thought I'd do a bit of acid base. We haven't done acid base in a while. So sodium hydrogen sulfate is room temperature and pressure is 24 decimeters cubed, and standard temperature and pressure it's rare that you'll get this. If you do get it, it's a tough one, and they'll probably show you, but it's 22.4 decimeters cubed per mole. But room temperature pressure is 24. Okay. My days. Right. Does acid and bases questions come up the most? They come up. It's not about frequency. Like you're gonna get acid base. You're gonna get kinetics of some sort. You're gonna get transition elements. You're gonna get a calculation of sorts, and you're gonna get a few wordy ones and some energetics. Like what you can't do, and I keep on saying this, what you can't do is predict. If anyone is selling you any prediction, they are selling you a lie. What you can do is say these topics come up with this much frequency. So they're selling you snake oil, don't believe them. Okay? It's a substitute for working. And the best preparation you can do is work and prepare for the exam. If they're selling you predicted papers, not true. Yeah, exactly. In my opinion, it's DW, it's worth doing as many past papers as you can and not necessarily the predicted ones. If you want to do the predicted ones and there is a decent enough mark scheme and it's not full of errors, then I would do it. But some of the stuff I've seen, even the mark schemes have errors. Not naming names here, okay? Cool. So at least with the actual resources from the exam boards, you know what you're getting. Those mark schemes are checked. KOCI shall remain silent on that one. So, sodium hydrogen sulfate is what this. Yeah, not even that, right? Like, you can't predict what's going to come up. I don't believe in that. Yeah, there were quite a few errors in the mark scheme. I only looked at the paper one, but there were quite a few glaring errors in the mark scheme. And make of that what you will. So I would stick to the stuff which has been checked. And that way it's not leading you up the garden path, right? So its acidic behavior arises from the presence of the hydrogen sulfate ion, which is a weak acid in aqueous solution. Write the chemical equation that represents the dissociation of HSO4-. Okay, so I've got HSO4-. For the paper. Thank you. Right, so that splits up into H plus and SO4, 2-, and done. Cool. Any questions? Are we good? That's a nice 1 marker. Let's go. Here's our friend. Laters. Okay, 5 markers. Yeah, Chloe, I just left 7, however many lines, because I couldn't be bothered to change the formatting. Right. I've got a solution of sodium hydrogen sulfate, and it's got a pH of 1.13. It tells me the pKa value. I've got to calculate the concentration of sodium hydrogen sulfate in grams per decimeter cubed. Yes, it's reversible because it's a weak acid, Shuendu. So, where am I going to start? Before I even find Ka, what am I actually going to do? I'm going to write my expression for Ka. So my expression for Ka is this. Okay, so let's have a look. Why is my lesson on Saturday? Because I couldn't do Monday's lesson, so I'm going to rearrange it for a Saturday. Remember, you can watch it whenever you want, so you don't need to wake up at that time. But the early bird catches the worm. Right. So in effect, I've got Ka. Is there any other information that I have? Well, I've got the pH, and the pH is not directly, but indirectly giving me what? It's at 9 on Saturday. Yeah, absolutely. It's giving me H plus because H plus is equal to 10 to the power of minus pH. So let's start writing a few things down. So I know this term, but hang on. I don't know what the sulfate term is, do I? It's a weak acid, right? It's the same. Yes, exactly. Good. Nice, nice. So I know that one as well. So what I'm going to say is let's simplify this to Ka is equal to H plus squared all over HSO4 minus. Yep, absolutely. So what term am I rearranging for? Let's rearrange first. Let's find our unknown, then we can start plugging in values. So clearly I am rearranging for the denominator. So this becomes HSO4 minus, which is equal to H plus squared all over Ka. Done. Okay, so now let's plug in. So my HSO4 minus concentration is equal to H plus. So my H plus is equal to 10 to the power of minus 1.92. So what's that? Do we get 0.0120226? No? Oh, why did I put 1.92? That's pKa. Silly, silly. So it should be minus 1.13. 10 to the power of minus 1.13. That looks sensible. 0.074? Okay, so then to get Ka, that's 10 to the power of minus 1.92, because I've got pKa. Does that make sense? Hopefully that looks good. So Ka is equal to 0.0120226. Okay, cool. So now I'm just going to bung these in. So that's 0.07413 squared all over 0.0120226. So what do we get? Do we get 0.45 or something? I get 0.45708. And I did a bit of rounding. Yeah, cool, wicked. So then where do we go next? So what I'm thinking is all of that came from my sodium hydrogen sulfate. So my sodium hydrogen sulfate, when I stick it into whatever, it dissociates into Na plus and HSO4 minus. So I have to determine the concentration of my sodium hydrogen sulfate. So what is that going to be? Yep, 1-to-1, absolutely. So to determine, so I've got the concentration is going to be the same, and I want it in grams per decimeter cubed. So what do I do? How do I go from mold to mass? Times it by the MR, absolutely. So that's going to be 0.45708 multiplied by the MR. So what is the MR? 32 plus 64 plus 24. Is it 120? So times that by 120, what do we get? Do we get 54.849? There might be some rounding errors, but if we say 45.85 grams per decimeter cubed, there or thereabouts, that's good enough. Cool. Sorted. Right, what do we think? Nice or horrible? Okay, so we've got 0.45708 moles per decimeter cubed. Now I don't have any data about the volume, okay? So I don't have any data about the volume. But because it's a 1-to-1, I can assume that the concentration of this was also the same, right? So then remember, if I'm trying to find, if I've got the mass concentration is, oh, so the mass equals the concentration times the volume if it's in grams per decimeter cubed, okay? So I know the concentration. In fact, what do I know? I am trying to find the mass concentration, so I can't use this. I can't use that because I don't know the volume and I don't know the mass. But I do know the concentration in moles per decimeter cubed, okay? And this is another trick that we can use. If I know the concentration in moles per decimeter cubed, I can work out the concentration in grams per decimeter cubed because how do I go from mold to mass? Multiply it by the MR because the mass is equal to the number of moles times the MR. So what I do here is just multiply the number of moles by the MR to go to mass. Does that make sense? You see why I've done that? So I couldn't do anything with this. So then I know that the moles per decimeter cube concentration is to go straight from moles to mass, I simply multiply the number of moles by the MR and done. Cool. Let's go. Do we need to do this little measly 2 marker? I mean, we know what the assumptions are. What are the assumptions? We'll just say it. What are my 2 assumptions here? We need to do it. Okay, fine. So we're going to say that the HSO4 concentration initial is equal to what? My HSO4 minus concentration at equilibrium. Why? Because the ionization is very what? Is very small. Okay, so that's assumption number 1. And what's assumption number 2? It's a weak acid. So what we can assume in a weak acid is that my initial acid concentration is the same as my equilibrium acid concentration because it's a really small extent of dissociation. Yeah, absolutely. And the second assumption that we can make is that my hydrogen ion concentration at equilibrium is equal to my sulfate ion equilibrium, my sulfate ion concentration at equilibrium as well. So what we're really saying is this means that only the HSO4 minus is dissociating. But you could say the ionization is negligible. KBM is revising hard as we speak. Right. Because what does that, there's quite a lot in that second statement. Because what do we actually know happens to pure water? That we ignore. Yeah, absolutely. So what we're saying is we're ignoring the hydrogen ions, really small extent of hydrogen ions that are due to the ionic product of water, i.e. the autoionization of water. So we ignore these. Why do we ignore these? Because roughly what is their concentration? 1 times 10 to the minus 7. So if I add 1 times 10 to the minus 7 onto, I don't know, 1 times 10 to the minus 4, what is my value of 1 times 10 to the minus 4? Can we still approximate it to be 1 times 10 to the minus 4? Yeah, it's so tiny, it makes very little difference to the overall hydrogen ion concentration. That's the whole point of doing this. Exactly. Because this is very small in comparison to this. Cool. Yeah, big difference between those in terms of order of magnitude. Right. Let's go. What is meant by the term buffer solution? So it's a solution that resists changes in pH, resists changes in pH when small amounts of H plus or OH minus added. Cool. Done. Let's go. Okay. Don't worry, Tuba. All good. So we've got to prepare a buffer solution. Or it's prepared by dissolving some number of moles of the hydrogen sulfate and some number of moles of the sodium sulfate in distilled water, making up a final volume of 1 decimeter cubed. Okay, so this is good because I don't have to do any concentration calcs, right? So what I'm going to do is write Ka because I want to work out what I need to know what I'm working out. From Ka, I can do that. Okay, let's go through each variable one by one. Do I know Ka, yes or no? I know Ka. I do, because didn't I have it previously because I know pKa? No, no worries, all good. So I know it because I had it previously. No, it's fine. It's not on the page. You will have it on the page in the actual question. So from the question, I've got that many moles of sodium hydrogen sulfate. So do I know the sodium hydrogen sulfate concentration, yes or no? Because you're young and it's meant to be here in your brains. Yeah, absolutely. I know that one. And then do I know the sodium sulfate concentration? Yeah, I know the sodium sulfate concentration as well, which is this one. Okay, so if you do it like this, you can easily work out what variable you need to rearrange for. So we are rearranging for H+, which is going to give us the pH of the buffer, right? So if we rearrange for H+, H+ is equal to Ka times the hydrogen sulfate concentration all over the SO4 2-. So then now we plug in the numbers. So what was Ka? Does anybody remember what Ka was? I'll quickly do it. 10 to the power of minus 1.92, if I'm not mistaken. So 0.012023 multiplied by the hydrogen sulfate, which is 0.75 over 1, if you want to do it that way, all over the sodium sulfate. Oh, wait, that's sodium sulfate. That should be 0.5. No, tell a lie. This is, I'm bugging. That should be hydrogen sulfate, so it should be 0.75. Okay, and then all over the sodium sulfate, which is this one. So the sodium sulfate is that value, which is 0.5 over 1. Okay, so what happens to the volume terms? Exactly. So what happens to the volumes? They cancel out. So what do we get as our hydrogen ion concentration? Okay, what do we get? If we all get the same, it's correct. The thing is, it's not even, it's outward now. It's so irritating. But what can you do? Yep, so I get 0.18034 moles per decimeter cubed. So then I need to find the pH, and the pH is the negative log of that value. So what do we get? So 1.74. Yeah, 1.74. 3 marks. Sorted. No dramas. Okay, we'll do one more and call it time. Cool. So it's a 4 marker where they add some stuff to the buffer. Okay. Let's do chem until 8. Well, I've got to get home, so as much as I'd love to, might not be able to do chem till 8 today. I can't remember when the crams start. Can't remember when the cram starts, but we might go on a bit if you want cram to go on a bit. So I've got some volume of HCl, which is separately added to 2 different solutions. 1 decimeter cubed of distilled water and 1 decimeter cubed of the buffer described in part B. Okay, cool. So where do we go? Nice question. Exactly, Tuba. He's probably asleep though. Well, probably not yet. What? Dav Jr. is probably not, in fact, definitely not asleep. Right, let's go. So adding 0. This number of moles of HCl to two different solutions. So 1 decimeter cubed of distilled water. Okay. He's not there yet. He's not there yet. You have no clue what to do on this question. Yes, you do. What are we going to do first of all? So I've got HCl. I know it's a strong acid. So it splits up fully into H plus ions and Cl minus ions. Okay. So don't need an ice table for this. Don't need an ice table for this. So I know the number of moles of HCl that I add. And I also know the volume of which I'm adding it to. So what's my days? So what's the volume? That's the number of moles. What's the volume? The girl's not even in reception yet. Yeah, it's 1 decimeter cubed. So the concentration in moles per decimeter cubed is going to be 5 times 10 to the minus 3 over 1. So the concentration is what? What? Agreed? Yeah, okay, so that's the concentration of HCl. So what's the concentration of H plus? Yeah, it's 5 times 10 to the minus 3 moles per decimeter cubed. So if I know the concentration, what can I work out? I know the concentration of H plus, so what quantity can I work out from that? Let's work out the pH. So the pH is the negative log base 10 of the hydrogen ion concentration. So what is that? Do we get 2.30? A log is something that you go and sit on after you leave this lesson. Right, let's go. Where do we go next? What we do? Sorry, it's the scribbles as well. I was like, not in the mood. Right, where do we go next? We always quote pH to 2 decimal places. So now let's work out the pH change in the other one, okay? So we're adding the same number of moles of HCl, but we're adding it to 1 decimeter cubed of the buffer solution. Okay, cool. So let's work out. We know what the pH was originally of the buffer solution, not a problem. How do we do this one? So if I write out HSO4 minus goes to H plus plus SO4 2 minus. If I add H plus, remember in a buffer solution, I've got a large concentration of the weak acid and its conjugate base. If I add H plus, which direction is this going to shift in? Yeah, the left, absolutely. So I've got to go back because I need to know how much SO4 2 minus I have. So how much SO4 2 minus do I have? Okay, cool. That's actually straightforward. So then what I'm thinking, let's write an equation for this. I've got H plus that I'm adding plus SO4 2 minus that it's reacting with. And what am I making? I'm making more HSO4 minus. So what do I need to do here? What did you get in A-level chemistry? I got a U star, correct. So I know what this is. That's 0.005 moles. Now it's all in 1 decimeter cubed of the buffer, so I can just work in moles. So my SO4 2 minus was 0.05, was it? Or 0.5. And my HSO4 was 0.75. What's the hate for, Nafisa? What's the hate for? Can't believe it. Right, so what do we do here? Nafisa is getting brave. You know that. Did I time out her alternative account? I see. Well, I can do her main one as well. It's not a problem. Right, tell me what to do here. You should think she's big. Okay, so which one's my limiting reactant? So which one's the limiting reactant? Yeah, H plus. So that's going to go down by the same amount. So that's going to go down by 0.005. That's also going to go down by 0.005, and that's going to go up by 0.005. Okay, so what are my new concentrations? Concentrations, moles, doesn't really matter here. Yeah, this one's an ice table. So we're going to have none of that left. So what is my SO42 minus going to be? Yep, 0.495. Well, it wasn't for this first one. You don't need an ice table for this one, though, do you? So for the second one, you do. So then for the second one, 0.75 plus, we get 0.755. Cool. All right, so now we're in business. It's all right. I'm zen. It's okay. So because it's 1 decimeter cubed, I can divide that by 1 and I can divide that by 1, but it doesn't matter here, okay? So where do we go next? Nafisa, you're in the wrong place. This is business. So what do we do next? I'm trying to find the pH. So the pH is going to be Ka times HSO4 minus all over SO4 2 minus gives me H plus. Yeah, so you can do all of this in moles, or you can put in the volume aspect. Because it's 1 decimeter cubed, I can divide all of it by 1 decimeter cubed, but they'll cancel out anyway. Does that make sense? Yeah, so if you want, you can leave them in. So then where do we go next? What's Ka? 10 to the power of minus 1.92. So if I sub in 0.012023 multiplied by my hydrogen sulfate, where do we go? 0.755 all over 0.495. Okay, what do we get as our hydrogen ion concentration, people? Why is Nafisa being nice? Divided by 0.495. Cool, that looks good. So then what do we get? So H plus equals 0.01838, and then the pH is just the negative log of that. So the answer, bosh. 1.74. Done. Okay, and let's see if that makes sense. So let's see if this makes sense. My original pH was 1.74. Whoa. I added some H plus and it's still 1.74. So has the pH changed? Yeah, so we'll have a look at the buffer. Now, it does ask for the change. So technically, what should I do? 1.74 from the original value. Take away your unrounded. So was my unrounded, whatever it is, what the previous answer was, but it changes by about what? So pH changes around 3.35 times 10 to the minus 3. So it's so small, but put that in if you want. But that is the pH change. But it is tiny. So really, really small. Okay, and that's it for 5 marks. That was so dead, respectfully. Wow. How do you know when to do an ice table? So, when you're doing a buffer and you're adding one thing, either the H plus or the OH minus to the buffer solution, you're probably going to have to do an ice table to work out what is in excess and what's in limiting amount. Just to say you hate me. What does one say to that? But before we go, is everybody happy so far? Good stuff, good stuff. Okay. Okay. But it's the limiting reactant from what we add. So we're adding some extra H plus. So if we're adding some extra H plus, then this concentration changes and this concentration changes. So then if we have a look at this, we've still got some H plus there, but the H plus there is from what? That's from the original. The fee says see you later. So that was from the original dissociation. Does that make sense? So the extra H plus that we added got mopped up by these guys. Yeah, exactly. So the extra stuff that we add gets used up. I see the question that you're asking. So what you're saying is, well, you're alluding to this. Tell me if I'm mistaken. So if I add extra OH minus, what is the OH minus going to react with? So the OH minus reacts with the HSO4 minus to make SO4, 2 minus, and H2O. Now, if the OH minus is in excess, if this is in excess, what do we do? Absolutely, we use KW. If it's not in excess, if it's limiting, what do we do? Well, then the concentration of the HSO4 minus that we see in the Ka expression is going to change. The SO4 2 minus concentration, which we see in Ka expression, is going to change. So then we use Ka because that ratio affects the H plus, but not by much. Yeah? And remember, if we're adding H plus, by the way, it's not going to be, it's very unlikely it's in excess because it resists small changes in pH. Does that make sense? The Saturday lesson should be the exam revision one. So it should be, so it's Monday's lesson that got rescheduled. So it's Monday's lesson that got rescheduled. So have a look on Monday's teach floor or the exam revision teach floor, and you should see the rescheduled lesson there. Cool. Good stuff. Nice questions today, and I'll catch you guys on Saturday. Is there anything you want me to do on Saturday? Because I was planning to do alkanes and finish up all Year 12 organic. Okay, cool. We'll do some Year 12 organic, and I'll put some extra Year 13 stuff in, some kinetics and some Arrhenius stuff as well. Yeah? An A level. What is an A level? That's quite deep. And on that note, and on that bombshell, I will catch you guys on Saturday. See you later. Ignoring. Bye.